We're going to continue with Chapter 18 and talking about sampling distribution models. Specifically today, we're going to look at sampling distribution models for proportions, so dealing with categorical data, the fact that the mean is going to be the true proportion and the standard deviation is the square root of PQ over N. Starting with the just checking, you want to poll a random sample of 100 students on campus to see if they are in favor of the new student center. If you imagine all the possible samples of 100 students you could draw and you make a histogram, what shape would it have? Now again, each student is one trial. So 100 students makes one sample. If you were to sample those 100 students as many times as you could possibly think of, and then take the proportion of students in favor and make a histogram, it would end up having a normal shape. 2, where would the center of the histogram be? Well, remember that the normal model will end up coming together in the middle at its mean, which would be the true proportion. So in this particular case, it would be the probability or proportion of all students who are actually in favor of the new student center. So for the rest of the video, we're really just going to be looking at examples using the sampling distribution model for proportions specifically. Looking at our first example, of all the cars on the interstate, 80% exceed the speed limit. We want to know what is the distribution of the proportion of speeders we might see among the next 50 cars. So to break this down, our proportion P is 0.8, so that means Q, which is 1 minus P, is going to be equal to 0.2. And then our sample size is 50. So to show the distribution, we really just show the normal model using the 68, 95, 99.7 rule. In order to do that, we need to find our standard deviation. So remember that the standard deviation for proportions is the square root of PQ over N. So in this particular case, the standard deviation would be the square root of 0.8 times 0.2 over 50, which equals 0.06. Then we're going to draw the normal model where our center is our proportion at 0.8. And we're going to have 68% fall within one standard deviation, so from 0.74 to 0.86. 95% fall within two standard deviations, so 0.68 to 0.92. And then 99.7% fall within three standard deviations, which would be from 0.62 to 0.98. So whenever they're asking you for what the distribution would be, you can just go ahead and use the 68, 95, 99.7 rule to show that distribution. Looking at our second example, suppose that about 13% of the population is left-handed. A 200-seat school auditorium has been built with 15 lefty seats, so desks that are designed for a left-handed student. In a class of 90 students, we want to know what is the probability that there will not be enough seats for the left-handed students. Breaking this down, we know that the population proportion is 0.13 and our sample size is N. If our sample proportion is 0.13, then Q is 0.87. In order to calculate our z-score, we're going to need two things: our mean, but we also need to know our standard deviation. So our standard deviation in this case is going to be the square root of 0.13 times 0.87 all over 90, which ends up equaling 0.035. Now remember that our z-score equation is x minus our mean over our standard deviation. Well, a better way to write this is going to be to say that it's our p hat minus our p over our standard deviation. So our sample proportion minus the population proportion over the standard deviation. So I know my population proportion and I now know my standard deviation, but I also need to know my sample proportion. So the original question is asking us that out of 90 students, what's the probability that we won't have enough seats if there are only 15 seats? So in other words, out of those 90 students, what's the probability that there's more than 15 people who are left-handed? So our sample proportion that we're going to use, p hat, is going to be equal to 15 out of 90, which is 0.167. The reason why I'm using this is because if I draw the normal model, my population proportion goes in the center because that's the mean, which is 0.13. So the 0.167 would be up here, and if we don't have enough, then we're going to be above that proportion. So that's kind of our cutoff proportion. So to calculate the z-score, we would then have 0.167 minus 0.13 over 0.035, which ends up equaling 1.06. So then the probability that our sample proportion is going to be greater than 15 out of 90 is equal to 14.5%, or 0.41 or 0.145, excuse me. And that would be our final answer. So again, the reason why we're able to use the normal model here to calculate the probability that we would fall short is because of sampling distribution models. So what we're doing here is we're essentially pretending that we would take as many combinations of 90 students as we possibly can, and if we were to plot the proportion of left-handed students in the class into a histogram, it would end up following the normal model, allowing us to use z-scores to calculate probability. I actually did forget to do one thing with this problem, and that was actually make sure that we could use the normal model by checking our assumptions and conditions, and I want to go back now and do that. There are 3 conditions that we have to check. The first one is that it was a random sample, and in this particular case, it doesn't actually tell us that the sample is random, but there's no reason to believe that the 90 students is not random. So we can say that the 90 students can be considered random. And then we have the 10% condition, which means that our 90 students have to be less than or equal to 10% of the population. So in this case, as long as there are more than 900 college students, we'll be okay. And I'm pretty sure that we have more than 900 college students in the US, so that one's fulfilled. And then we have the success-fail condition. Now the success-fail condition tells us that we need to have at least 10 successes and 10 failures. So the number of successes would be 0.13 times your sample size, so your probability of success times the number of trials. In this case it's 11.7, and that is indeed greater than or equal to 10. And then our number of failures would be 0.87 times 90, which is 78.3, which is also greater than or equal to 10. So all 3 of these are met. So doing what we just did was okay. Again, every time you do one of these problems, you have to actually check your assumptions and conditions, just as I did here. Looking at our last example, we're looking at groovy M&Ms. I believe we've talked about groovy M&Ms before, and they're supposedly supposed to be all speckled, so they called them groovy. But groovy M&Ms are supposed to make up 30% of the candies sold. This is not current. In a large bag of 250 M&Ms, what's the probability that we get at least 25% groovy candies? Again, in this case, my population proportion, it's supposed to be 30, so my population proportion P is 0.3. My sample proportion, well, they told me that I want to get at least 25%, so my sample proportion is going to be that 0.25. And my sample size, N, is 250. So I have almost everything I need to be able to calculate the normal model, but I need to calculate the standard deviation first. So my standard deviation would be the square root of PQ, so 0.3 times 0.7 over my sample size of 250, which equals 0.029. Now, again, before I go any further with this, I need to make sure that it is okay to use the normal model here. So again, I need to check my conditions, that it's random, and in this particular case, again, they don't tell us that the bags are randomly filled, but we're going to have to kind of assume that the bags are filled randomly. Then we have our 10%. As long as more than 2,500 M&Ms were made. We're good there. And then our success fail. So again, 0.3 times 250 is equal to 75, which is greater than or equal to 10. And 0.7 times 250 is equal to 125, which is greater than or equal to 10. So again, since all three of these conditions are met, then we can go ahead with the problem. So then in this case, I need to calculate a z-score. So I would have my sample proportion minus my population proportion divided by my standard deviation, which gives us a z-score of negative 1.72. So looking at the normal model, 0.3 is here, 0.25 is here, and I want to know that we get at least, so I'm shaded this area up here, so I'm looking for above, so then the probability that my proportion is greater than or equal to 0.25 is equal to 0.957. So we have a 95.7% chance that we get at least 25% M&Ms being groovy M&Ms. Excuse me. All right, that is all I have for tonight. I hope you guys have a good night, and I will see you tomorrow.